I did want to start by telling you a little bit about what the field of quantum information is about. So trying to figure out how much is enough time. So the field of quantum information obviously is about quantum mechanics. And in particular, it's about the idea of thinking of quantum states as a new form of information, and of processing those quantum states in ways that we traditionally process classical information. So, so in particular, one of the main goals of the field, obviously, is to build a quantum computer. A quantum computer has in its memory quantum states that can be in superpositions and entangled states, and does computations on them just like a regular classical computer does computations on a string of bits. And building a quantum computer is a very big technical challenge. There's a lot of experimental progress that's been made over the years, but we still have a long way to go before we have a quantum computer that's really a useful thing. I mean, obviously, I'm not going to go too much into the experimental stuff. Actually, I won't go into anything about building a quantum computer because I'll be away. Aggie will do that later this week. But there's also an important theoretical side of coming up with new insights as to how to improve the implementations or come up with different kinds of implementations. So of course, the reason we want to build a quantum computer is that it can do some stuff that we can't really hope to do with a regular classical computer. And so the headline there is quantum algorithms, which can solve some problems much faster than a classical computer can solve some problems. So one aspect of the field of quantum information is to figure out what exactly a quantum computer is good for. So we know some algorithms, but probably there's more that we haven't discovered yet. So trying to understand what those algorithms are, and maybe trying to, for instance, find evidence that certain problems can't be improved with a quantum computer. That's a big topic of theoretical investigation. But it's not just about quantum algorithms. There's other kinds of quantum protocols that we can discuss as well, such as quantum cryptography, which is a method of transmitting quantum states in such a way to give extra secrets, to improve the secrecy of some classical message that you'd like to send. So that's an example of something that's, so quantum computer is something you do just in one place, right? You have the computer, you solve some problem. Whereas quantum cryptography is an example of a quantum communications protocol, where you have people at different places that are sending quantum states at least one direction between them. OK, so another aspect of the field of quantum information is maybe a more purely theoretical one, which is trying to understand the properties of quantum information and how it differs from classical information. So if you go into literature, you'll see a lot of examples of, here's what quantum can do compared to what classical can do. Like quantum algorithms is already an example of that, right? Where classical algorithm can do this, a quantum algorithm is better, or maybe it's not better. And trying to understand the shape of these various kinds of advantages and disadvantages of quantum information helps give us a better insight into quantum mechanics. And so that insight then can pay us back when we take these insights about quantum information and quantum mechanics and try to apply them to other areas of physics. And that's something that's starting to be a big deal nowadays. So for instance, there's a whole field of cold atoms. which kind of grew out of experimental advances in making Bose-Einstein condensates and trapping them in optical lattices, and applying quantum information ideas about using quantum systems to simulate other quantum systems and to manipulate quantum systems in the way that I'll talk about in the next few days. Combining that, again, with the need in condensed matter to get better simulations of different kinds of systems, they can write down models of different things, but then they want to know how they behave, right? And you can analyze those theoretically, computationally, but ultimately there's a big difficulty in doing it on classical computers. A quantum computer or quantum simulator would presumably do much better. So that's kind of one area that's really quite a large field now, is kind of born partially out of quantum information ideas. But quantum information is also finding its way into kind of more standard mainstream things. I mean, condensed matter has adopted a lot of quantum information ideas, for instance, the study of topological order. Quantum error correcting codes are very closely connected with topologically ordered systems, for instance. Even string theory has started absorbing some quantum information ideas in recent years, and people writing, entanglement, entropy, and holographic systems, studying black hole firewalls in terms of quantum information ideas. So it's not something that is kind of isolated. It's something that can affect almost all of physics, anything that has quantum in it, which is quite a lot. And in fact, it's not just confined to physics. I mean, because we're comparing quantum information with classical information, sometimes studying quantum information can give us extra insights into the way classical information behaves, or help us prove new things about classical information, and therefore can help us gain some insights into classical computer science. So that's kind of the overview of quantum information. I'm not really going to be touching too much in this course on this last topic. There's simply not time. I'll be concentrating on the core ideas of quantum information, which are, what is a quantum computer? What is, how do you build a quantum computer? What do you do with a quantum computer? With quantum algorithms, quantum protocols, and maybe a little bit about the general properties of quantum information at the end, assuming I have time. OK? Maybe questions to just start off? OK, I haven't really said much yet anyway, so this OK, so then let's get started. So of course, the basic unit of computation classically is the bit, right? That's the basic unit of memory. So a bit has values 0 and 1. And so in the quantum case, we want to generalize that to a quantum bit, or what's usually called a qubit. And the qubit can be in a superposition of 0 and 1. Right? So the 0 and 1 now form the basis states. So we put kets around them. And then the general state is going to be alpha 0 plus beta 1. And of course, generally this is normalized, so alpha squared plus beta squared equals 1. But most of the time, we don't bother with that, right? It's too much trouble to keep track of that usually. And so you'll see things like 0 plus 1 in this course frequently. So this qubit lives in a two-dimensional Hilbert space. So this is something that's kind of characteristic of quantum information, which is not quite so common in the rest of physics, which is dealing with finite dimensional Hilbert spaces a lot. Now, that's not essential. You can do a lot of these quantum information ideas in infinite dimensional Hilbert spaces. But this is kind of a nice simplifying assumption. And it corresponds very nicely with what happens in classical computers, where you have just a finite number of states. And here you have an infinite number of states, but it's only a finite dimensional system. It makes everything a little bit easier to deal with. Now, this, of course, is just what happens if you have a single bit or a single qubit. But to make any kind of interesting thing, we're going to have multiple bits and multiple qubits. So classically, multiple bits will be some sort of n-bit string. So for instance, 0, 1, 1, 0, 0, or, sorry, 0, 1, something like that. Again, in the quantum case, the classical bit strings will form the basis for the Hilbert space. So the basis states are labeled by these classical bit strings. In general, we can have a superposition of different bit strings. That's what makes it quantum, right? So we can have a state like, did I have an example? Whatever. So this is a nice example, 0, 0 plus 1, 1. And so one reason this sort of state is interesting, particularly interesting from a quantum perspective, is that it's not just a tensor product of two individual single qubit states. So for instance, you have 0, 1 plus 1, sorry, 0 plus 1, or tensor 0 minus 1. This is another example of a 2-qubit state. But this one can be broken down, and you can kind of think of this as one qubit and this is another qubit as totally separate things. Right? Whereas here, you have an entangled state. And a lot of the interesting aspects of quantum mechanics start to pop up when you have entangled states. So let's see. So putting this together, since we have the basis states labeled by bit strings, there's a total of 2 to the n possible bit strings. So n qubits have a 2 to the n dimensional Hilbert space. Okay? So that's mostly what we'll be dealing with in this course, this 2 to the n dimensional Hilbert space. Okay, so the next important unit of computation is the idea of a gate. So it's not just enough to have a string of bits in your memory for a classical computer. You want to manipulate those bits. You want to change them. And so there's various models of computation that people have talked about. But one that's kind of convenient and the one that's most used in the field of quantum information is the circuit model. And so in the circuit model, we break up the computation into fundamental units, which are called gates. And a single gate will act on only a small number of bits at once. Like 2 or 3, something like that. And yeah.
You can have gates acting on like the entire system.
Yeah, in principle, you can have a gate acting on an entire system. But normally when we talk about gate, we're talking about a fundamental gate that's acting on only a few bits at once. It's not an intrinsic part of the definition, but it's kind of the usual connotation. And then in the quantum case, of course, so then we put these gates together into a bigger circuit, a sequence of gates. And that's our kind of more general computation. So circuit. And so in the quantum case, of course, we have quantum gates. That's the usual thing that happens in quantum. In quantum information, every word gets quantum stuck in front of it. So we have quantum gates, which of course deal with qubits, and you can have quantum circuits, which will then be sequences of quantum gates. Was there a question in the back somewhere? No? Okay. Okay, so let's start to talk about gates. So the first thing that we should think about is actually classical gates. So one thing that's a bit different about quantum systems than classical systems, normally in quantum computation, the gates we talk about are in fact unitary operations. Okay? And the thing about unitary operations is that they have inverses. Well, that's one of the things about them. Which means that any computation you do is going to be reversible, right? You can do the unitary, or then you can do the inverse of the unitary, and get back to where you started. And actually, that's not necessarily true of classical gates that people usually talk about. So let's think about reversible classical computation first. So classical computation, some gates that you would think about are kind of naturally reversible. So an example of that is the NOT gate. So we can write this truth table for the NOT gate. So the input and the output. So if the input is 0, the output is 1, right? So you can think of 0 and 1 as true and false, if you like. And if the input is 1, then the output is 0. So the NOT gate reverses the input. Okay? And clearly this is reversible, right? If you do it just twice, you get back to where you started. When we talk about classical circuits or quantum circuits, we frequently like to draw something called a circuit diagram. And let's see here. So let's go over here. So in a circuit diagram, we'll have a bunch of lines. And so each line represents a bit, because I'm talking about classical computation. And time goes from left to right. So an example of a circuit which is just going to have one gate in it, which is for the NOT gate, is this. Okay? So we have the input here on the left, A. Then we do this NOT gate, which is the circle, crossed circle. And then we get an output, which is not A. So, or A plus 1, mod 2. There's another way of doing it. Okay? And you could build up, if you want, a circuit that consists of multiple gates, for instance, like this. So this would take the input and do 2 NOT gates, which, as I've said, gives you back the input again. So the input and the output in this case, this is just a trivial circuit. Okay? So what else do we have? So another gate that's kind of easy to make reversible is the XOR gate. So here it's going to take 2 bits as input. Okay, and then the output is going to be the XOR of A and B. So if we have 0, 0 as an input, the XOR of the exclusive OR is going to be 0. If we have 1, 1 as input, the exclusive OR says only one of them should be 1. So that's 0. And in these cases, we have the output 1. Okay. Now, this, if you take it like this, is clearly not reversible, right? Because there's only one output bit. You have like 2 1s here. You can't tell whether the input was 0, 1 or 1, 0. So you've lost some information. But if I just keep track of this first bit and don't discard it, now it becomes reversible. Why is that? Well, you see that this gate is just rearranging these 4-bit strings, right? So this one goes here, and this one's here, but these two get switched, right? So just by switching them back, in other words, by doing this gate again, once again, you get back to where you started. Now, reversible gate doesn't have to be its own inverse. It's just these examples, simple examples, happen to have that property. But the main point is that there is an inverse, that you can get back to the original state. Okay? So this XOR is also, in the quantum case, frequently called the controlled NOT gate. And the way we write the circuit for that is, well, there's 2 bits now. And so this first one is the control bit, and there's a black dot here. And then we have a line, and then one of these not, crossed circles. So that's a little circuit that looks like this. Okay? Is everything clear so far? Okay. Maybe I'll use another board. Okay, so now let's try a classical gate that's not so easy to make reversible. So what is that? Well, that's the AND gate. So what's the truth table for the AND gate look like? Well, again, it's something that takes 2 inputs. And the output, again, classically, normally you only think of 1-bit output. So that's clearly not going to be reversible. But even when we add in this A, it's still not going to be reversible. So what does this do? Well, consider the 4 possible inputs. So the AND gate basically is taking the product mod 2. So if both input bits are 1, we'll get an output 1 here, and otherwise we'll get an output 0. Okay. So again, clearly not reversible. But you'll notice even if we write down A here, it's still not reversible. Because both 0, 0 and 0, 1 have the same output, 0, 0. Right? So some information has been lost. There's no way we can go back from this to get this reliably, because we don't know which it was. Okay? So this is not a reversible gate. Nevertheless, there's a trick that we can use that's a little more sophisticated to make it reversible. Then we get something called the Toffoli gate. So the Toffoli gate, the trick there is not to just keep track of one of the inputs, but to keep both of the inputs as well as the output. So now it's going to be a 3-bit gate. And the outputs are going to be, well, so A and B are the ones we care about. C is kind of the extra one that records the answer. So the third output is going to be C plus A times B. So in the cases where C starts at 0, the output is just going to be the AND of A and B. And then we have the cases where C starts as 1. And then this is going to be the opposite, the NOT of A and B. So we have 0, 0, 1, 0, 1, 0, 1, 1, 1, 0. Okay? And now if you stare at this for a bit, you'll see that it's once again reversible. So again, actually, it's its own inverse. If you do this twice, we'll get back to where we started. Or you can just notice that these 8 things are all different. Right? So again, it's a rearrangement of the 8 inputs. Okay. I guess, again, we're switching kind of these two bottom ones. OK? So this is a trick. And while the AND is not reversible, Toffoli gate is reversible. So we still have that. When we're doing quantum computation, we still have the option of doing Toffoli gates. Well, I mean, I haven't told you yet how to do quantum gates or what a quantum gate looks like. But clearly, we want to kind of incorporate classical computation. Yeah?
What does the third column notation mean?
Yeah, so this is basically arithmetic modulo 2, because we're dealing with bits. So this is the plus modulo 2. It's also equal to the XOR, which I wrote up there. And then this is just multiplication. So 0 times 1 is 0, for instance, which happens to be the same as the AND. OK? Any other questions? OK, so let's see, I can fit one more up here. So the Toffoli gate has a similar kind of picture associated with it, gate network picture, to the CNOT. But because there's 3 bits, we have 2. So Toffoli you can think of as a controlled knot. So we draw it this way. And there's going to be 2 controls here and a knot here. You see, because this third bit gets flipped if both of these things are 1. Whereas in this picture, the second bit gets flipped if the first one is 1. So that's the idea behind the controlled knot name and behind these pictures. OK. So you can see that this trick that we use for the Toffoli gate can actually be used for any classical computation, right? Whenever we calculate some function, f of a, b, c, et cetera, we can make it reversible by keeping track of the inputs. So if we want to, if we have something like this, that's generally not reversible. But instead, if we keep track of the inputs like this, and then have an extra output bit, and you can do exactly the same trick, in fact, where we have an ancilla that's an extra bit that starts at 0 here, and in general gets XORed with this thing. This is reversible. Because by having these inputs around, we always know where we started. OK? But of course, I said we wanted to make circuits by putting together a bunch of gates. And this is telling you how to make the final answer reversible. But what we'd really like to do is to make circuits reversible. And of course, if we build up a circuit out of a series of individual gates, which are themselves reversible, the circuit as a whole is reversible. That's not a problem. But you see there's a kind of a bad side effect of doing that. So let's take, as example, this thing. We want to calculate the AND of A, B, and C. Right? So this is, in this binary notation, it's the product, A, B, C. So how do we do this? Well, so we start out with 3 input bits. To calculate the AND of A and B, well, then we have to convert that into a Toffoli gate, right? So we're going to do this Toffoli gate here by adding another bit, which starts out as 0. OK? And so now this one is going to be A times B. And then we want to calculate the AND of that with C, so we should do another Toffoli gate onto another extra bit here. And this gives us A, B, C as the output. And then these are not changed, so we still have the inputs. So you see, this is reversible. We've kept track of the inputs. and we have the output here, but we also have this extra thing. So this is a scratch bit that we use kind of in the middle of the computation. But at the end of it, it has some leftover information about what we were doing. And as you'll see, that's going to be a problem when we start talking about quantum computation. But at the moment, even just for reversible classical computation, it's kind of untidy. Right? We're leaving this mess around of all of these intermediate bits that we're keeping track of. So there's a trick to get rid of these things called uncomputing. The way that works is, well, we needed this input at this point, or this output, I should say, at this point, right, so that we could calculate the Toffoli gate here. But after that, we don't need it. So let's erase it. We still know what A and B are, so we can erase it just by doing another Toffoli gate here. Right, so what does the Toffoli gate do? It takes this thing, which is currently AB, and adds onto it A times B. So AB plus AB modulo 2 is 0. So the output here is now 0. We've cleaned up. OK? And so there's a general technique you can use to erase these scratch bits. So what does that look like in general? Well, suppose we have some circuit involves a bunch of bits. So I'm drawing it abstractly as this box here. OK? And so we start, we have bunch of different inputs here. In the process, well, OK, so some of them maybe started as 0. But in the process, we've generated some junk. Right? If it's a reversible circuit, we kind of kept track of the inputs as we wanted. I guess doesn't really matter at this point. But there are some outputs here. And maybe they've been changed as well. But down here is the answer. Okay, but we also have this extra scratch bit here that we want to get rid of. So how do we do that? Well, in the same way, we're going to kind of uncompute part of this input, or part of this calculation. So first thing we're going to do is we're going to copy this bit to another extra bit. Okay, so this one here is going to be the real output. And then we're going to take the C and undo it. OK? So because for classical computation, this controlled knot doesn't change what happens here, right? The value of this bit doesn't change any of these other bits either, certainly. What comes out here is going to be the same as what went in at the beginning. C and C inverse will cancel. But in between, we had time to copy the bit and get the answer, right? So this is a case where we've cleared all of the scratch bits. And this works for any circuit, any reversible circuit, right? It has to be possible to make this C inverse. OK? And of course, C inverse, C is built out of a sequence of gates. Each of them is individually reversible. So we can make an C inverse by doing the gates in reverse order, doing the inverse gates, I should say, in reverse order, right? Just as usual. OK? So any questions on this? Yeah.
So this can't generalize to quantum computation, though, because you can't just copy a bit. You can't just copy So
maybe I'll talk about that more. So it does in fact generalize. But for the moment, well, Yeah, for the moment, I'm just talking about classical computation.
Yeah.
And this will be a trick that we use for the classical parts of the computation. You're not necessarily going to do this for the general quantum computation. But yeah, let me get back to that sometime.
Yeah.
Okay? Okay, so in that case, let's move on, in fact, to quantum computation. And so the first thing I want to do is discuss kind of what the basic quantum gates are going to be. So quantum gate, as I said, is usually going to be unitary. And of course, to start off with, we're going to want quantum gates that correspond to the classical gates, so that a quantum computer is capable of doing the same things a classical computer is doing. We want it to be able to do more than a classical computer, but it should at least be able to do the same. And so how do we do that? Well, what we can do is we can take all of these classical gates that I've talked about, the reversible ones, and we'll convert them to quantum gates just by putting kets around them. So for instance, we have the C0 gate, and it will act on AB, the ket labeled by these 2 bits, AB, and give us the output labeled by A plus B. Okay. But because it's a quantum gate, it can now act on superpositions as well. So if we have C0 acting on the general 2-qubit state, well, the behavior on this, I mean, this only tells us what it does on the basis states. But then for the general input state, we can extend the action by linearity, right? Anything that happens in quantum mechanics should be linear. So that means that the C0 acting on the superposition is going to be alpha times the C0 on here, which is 0, 0, plus beta C0 on this, 0, 1, plus gamma C0 on this is 1, 1, and delta C0 on that is 1, 0. Okay? You see how that works? And similarly, we can do the Toffoli gate. So that'll take 3 inputs, or a 3-qubit system. And on the basis states, it takes ABC to AB, C plus AB. Okay. Now, it's sometimes convenient, of course, to write down matrices for these. So, for instance, the C0, well, it's acting on a 2-dimensional Hilbert space, sorry, a 2-qubit Hilbert space, which is a 4-dimensional Hilbert space. So it's going to be a 4x4 matrix. What does that 4x4 matrix look like? Well, it takes 0, 0 to 0, 0, 0, 1 to 0, 1, and it switches 1, 0, and 1, 1. So it looks like this, 1, 1, and then kind of the bit flip down in the corner here. Okay? And similarly, you can write down a matrix for the Toffoli gate. It's an 8x8 matrix, so I'll save myself some time not writing it down. But it looks similar, right? You have 1s down until the corner where you have the kind of the 1, 1 thing here, where you have this x bit flip. Okay. So good. So that gives us a bunch of quantum gates to start with. But these are just classical gates. And if we just make up a circuit that only consists of C0 gate and Toffoli gate and other classical gates like that, then we aren't really doing anything very quantum, right? We're just, if we start with the basis state, we'll always have the basis state. And so we could just forget about the kets and think of it as classical computation. So in order to really build a quantum computation, we want to have some gates that do interesting things to superpositions. So for instance, we can have the Hadamard gate. So what does the Hadamard gate do? Well, so we like to draw the Hadamard with a circuit diagram like this, with a box with an H in it. And it has the matrix 1 over root 2, 1, 1, 1 minus 1. So that means it takes 0 to 0 plus 1, again, ignoring normalization, and 1 to 0 minus 1. Okay? So it's probably not immediately clear, but if you do a little bit of a calculation, you'll see that the Hadamard squares to the identity. So it is, in fact, a unitary. It's H is equal to H dagger is the inverse. Okay? So this is a gate that creates superpositions. And because it squares to 1, if you start with a superposition 0 plus 1, you'll kind of destroy the superposition. That gives you the option of having interference, possibility of having interference. OK, so we also want to do stuff that manipulates those phases. So for instance, we can have a phase rotation gate, which we can draw, again, with a box. So this kind of cross-circle notation is useful just for knot. And we have the controlled knot. You put these controls on it. Kind of other quantum gates usually are put in some box with a label to indicate what the gate is. Let's see. If I go any lower here, that will be a problem. But this is OK? Yeah, OK. So the matrix for this phase rotation is 1 e to the I theta. And so what does that do? Well, on 0, it doesn't do anything. It just takes it to 0. And 1 goes to e to the I theta 1. And of course, if you have a superposition, alpha 0 plus beta 1 goes to alpha 0 plus e to the I theta beta 1. So one thing that's worth noting is that global phase, of course, has no physical meaning in quantum mechanics. So for instance, this gate here is really the same gate, up to things that don't matter physically, as a gate like this. Frequently, I write the theta over 2. Right, so I've taken out a factor of theta over 2 here, e to the I theta over 2. And so frequently, this r theta gate is actually called the theta over 2 gate. So for instance, the r pi over 4, where this angle is pi over 4, is called the pi over 8 phase rotation. And the history of that has to do with what physical system you want to think about doing it in. But that's not really important. OK, so now we have some examples of kind of real quantum gates. But it's not actually enough to stick with just unitary gates, right? Because in order to start a quantum computation, we need some way of getting the input. And in order to finish the computation, we need some way of measuring to get the output. So we're also going to have some non-unitary circuit elements. And those are well, there's state preparation circuit elements. So usually you have at least the capability of preparing the 0 state. Okay, so that just looks like this in a circuit, pretty kind of trivial. But you might have, as kind of your fundamental operations, you might have the capability to prepare other states initially. Normally, though, again, we'll talk about preparing single qubit states, or maybe in some cases 2 qubit states. So it's not going to be arbitrary states that you can prepare. But the point is, this is a non-unitary thing, right? Because it's taking, well, beforehand you had a zero-dimensional Hilbert space. You didn't have a quantum state at all. And now you have a state in a two-dimensional Hilbert space. It's a particular state, but nevertheless. So it's you can describe it as a CP map that takes a smaller Hilbert space into a larger one. But then, of course, the more interesting aspect is the other side, right? The measurement. And again, you can think of measurement in various different bases. But at a minimum, we probably want it in the kind of the computational basis, the standard basis, which is labeled by these kets. So if we have alpha 0 plus beta 1, we can measure and get, with probability alpha squared, we get 0. And with probability beta squared, we get 1. And so the kind of notational circuit element that people write down for this differs a lot. People use all sorts of different things for measurement. I frequently use something that just looks like this. Right? Looks like this. Okay, with a kind of you can think of it as a microphone broadcasting the output. Okay? Yeah.
So here you've put kind of all your computational or quantum computational complexity stuff into the unitary operators that you're putting.
Yeah, that's right. So I mean, so classically, certainly we need state preparation classically. Measurement is kind of a way of converting quantum into classical. And in this case, since I'm just doing it in the standard basis, there's nothing kind of extra hidden in that. Yeah. But certainly, as I said, you could imagine having the ability to prepare other kinds of states, like alpha 0 plus beta 1, plus 0 plus 1 is already a state, and measuring in other bases, and then you can do some more interesting quantum stuff with kind of just these things.
But from this here, if you were to restrict your class of unitaries, you'd start to cut back on the amount of the allowed quantum computation you can do, right?
Not necessarily. So that's something I'll get to probably tomorrow. Okay, so once we have these various different kinds of quantum gates and other kinds of quantum circuit elements, we can put them together to make interesting quantum operations and interesting quantum states. So, so for instance, there's that entangled state that I wrote down somewhere at the beginning, 0, 0 plus 1, 1. How do we make that using a quantum circuit? Well, it's going to be 2-qubit states. So we start out with preparing 2 individual qubits. And then what we're going to do is we're going to do a Hadamard here. So this state is now 0 plus 1. And then we do a controlled knot, like this. And then this output state is 0, 0 plus 1, 1. Okay? Why don't we go through so you can see how it works? So at this point, we have 0, 0. At this point, we have 0 plus 1 tensor 0, because we've only done a gate on the first qubit. And then at this point, at the end, what do we have? Well, what does the C naught do here? We can write this 0, 0, 0, 1 tensor, sorry, 0 plus 1 tensor 0 as 0, 0 plus 1, 0. And then, well, I don't really need to write it again since I already wrote it. But then what does the C naught do? Well, this control is a 0, so this does nothing. This control is a 1, so this gets flipped. And that's how we end up with this thing here. You see? OK. And in the tutorial, you'll get a chance to kind of play with some quantum circuit diagrams and see how this works in general. OK. So now maybe for the last topic, let me get back to this question of uncomputing and how it applies to quantum circuits. So it turns out, I mean, in the classical case, it's kind of just a convenience to get rid of these extra bits. But in the quantum case, it's really, really important to get rid of those scratch bits because they can decohere the state. You'll actually get different results if you do a quantum computation and you do the kind of the classical subroutines with or without erasing the bits. So let me show you an example of that. So let's imagine that we start with a superposition like this, 0, 0, 0 plus 1, 1, 0. And then let me apply the two different versions of this circuit, with or without this extra Toffoli gate. Okay? So what are we going to do? Well, we're going to have two extra scratch bits here that we're going to use, right? And so if we don't erase, what do we have? Well, this bit gets the AND of the first two ones, and this one gets the AND of all three. So the AND of all three in this case, in both branches, is 0. But the AND of the first two is 1 in the second thing. So we end up with 0, 0, 0, 0, 0 plus 1, 1, 0, 1, 0. Okay? And if we do erase, then what do we have? We have, well, this thing always ends up as 0, and this ends up as the AND of all three. So this is 0, 0. But in this case, we have 1, 1, 0, 0, 0. Okay? Now, it may not be immediately, I mean, these are clearly different states, but it may not be obvious to you that that matters. But it does matter. And the way you can see that is by looking at what happens if we trace out the fourth qubit. So what that means is we're discarding this fourth qubit because we're not going to use it again. It's just a scratch bit. It's junk. We don't care about it. So we're getting rid of it. And so let's look at what state we have left over for the other 4 qubits, the ones that we do care about. So maybe let's do this one first because it's easier. Well, what do we get? Well, in both cases, it's 0 here. So we get a pure state. 0, 0, 0, tensor 0, plus 1, 1, 0, tensor 0. Okay. But in this case, we don't get a pure state because the fourth bit is distinguishing between these two things. So if we trace it out, well, we'll get a density matrix. And we'll get the density matrix that is an incoherent mixture of this thing and this thing. So we have this mixed state. Okay? And so that's going to really matter a lot because pure states, a superposition like this, then later on you can do some sort of interference between these two branches. This mixed state, you cannot do that interference. Okay? So you know, if you try to run a quantum computation and you haven't erased these scratch bits, then you'll get these mixed states, you'll get decoherence, you won't get the right answer in the end. Whereas in the case where you did erase, you will get the right answer. Okay? So that's why it's really important to do this. And maybe this then is a good point to get back to that question. So how does this thing work when we're doing it with quantum circuits? Okay. So imagine we have something like this. We have some ancilla qubits, but now they're qubits, I guess. So they're all kets here. And we do some quantum circuit like this. And then let's do the C naught here. So this is a little bit tricky, as it turns out. But let's imagine that we're restricting attention to the case where C is basically just a classical circuit implemented using these quantum tricks. Okay, so it's composed of C0s and Toffoli gates and stuff like that. And so if we do that, right, then what happens? Well, at this point, because we started with a basis state, we did a classical circuit, we have, again, a basis state. Okay, so this thing here is going to be some classical bit string inside a ket. So I don't know, let's call it y0, y1 through yn. Okay, which is a tensor product of single qubit things. And then when we do the C0, what does the C0 do? At this point in the computation, well, we have y0, y1 through yn, and then we added this extra 0 bit. And the C0, this is a bit, so this will become yn as well. Okay? And so then what does the C inverse do? Well, the C inverse, remember, is the inverse of this classical circuit. So what it's going to do is going to take this bit string and send it back to ABC000. So then here we have yn. And so, in fact, we do, in fact, get back all of this stuff erased. And it seems to work. Okay? Now let's imagine what happens if we do this on a superposition. Okay? Well, for each, this is one of the basis states. Right? So if we do it on a superposition of things, okay, let me change these to x's. So if we do this on instead a superposition of x inputs, okay. Well, for each basis state, we get out this thing here, right? So instead of the basis state, we're going to get out a superposition again by linearity. Get a sum over x of x, zeros, and then this yn, which is really a function of x. Okay? So as long as we're doing just classical circuits here, the inverse works correctly. We uncompute everything as desired. And we get the desired superposition. Once we trace out these extra scratch qubits, we get the desired superposition. That's an entangled state between this output bit and the input bit. Now, when C is really a more interesting quantum circuit, then this thing doesn't, even if this is a basis state, this doesn't have to be a basis state. And then this doesn't necessarily invert correctly. So there's some kind of more sophisticated tricks that let you deal with situations like that. But in the quantum case, you don't normally have the scratch bits at all, because something like the Hadamard doesn't have any scratch bits associated with it, or the phase gate doesn't have scratch bits associated with it. So really, this business of erasing the scratch bits, that's mostly specialized to make the reversible versions of classical gates. OK, so why don't I end there for today? Are there any questions? Yeah.
Are reversible classical computations as powerful as general classical computations?
Yeah, that's right. Oh, yeah, OK. So tomorrow I'm going to talk about universal gate sets. And you'll see that the gates that I told you already are enough for a universal classical gate set. But the main thing, the main observation is that just to see that reversible and non-reversible are equally powerful, is to look at this line here, right? So the kind of general classical computation takes some input bits and gives you an output, right? Some function. And so there is a reversible operation that does the same thing, basically, by doing this, right? It takes the input bits and then it adds on an extra bit that's the output. Okay, this is reversible because, well, you still have all the inputs here, so you can easily go back to the start. Now, what's not nearly as obvious is how to make this operation by putting it together from these individual gates. But it's, of course, not obvious how to make this by putting it together from individual gates either. So that's something I'll talk at least a little bit about tomorrow. Okay? Other questions? Okay. So then see you tomorrow.